Okay, so let me share the sort of problem statement here, but you already have yours, so you can take a look at it. Okay, so let us start this particular problem. In this problem, there are two loops which are given, loop A and loop B. Many times in your programming assignment, you would be writing loops like this. Now the question is, which one is the right way of writing the loop and which one is the wrong way of writing the loop? When I say the wrong way, means there is technically nothing wrong. Mathematically, they are both correct. But for the convenience of cache, one of them is really good and the other one is not so good. So here we are looking at one large matrix which is given. It is not too large, but it's reasonably large. It is 128 by 64 matrix. So can you tell me, maybe through the chat window, or you can speak up, how many rows would be there in this particular matrix and how many columns would be there?
128 rows and 64 columns.
Okay, that is one answer. Okay, I believe others agree with it. So let's say this has got 128 rows by 64 column matrix. And both of them would have a similar thing. But the one which I would like to draw your attention is that matrix is stored contiguously in memory in row major order. Now, this is not a statement which is specific to this particular problem. In programming languages like C, C++, or Python, the matrix is always stored in a row major format. That means it is stored row by row. Whereas in old programming languages like Fortran, they were using storing the matrix in a column major format. So, they were storing data in terms of columns. So now let us see. Now, the question which is asked of us is that it is a 4 kilobyte direct map cache. It is a data cache with 8-word cache line. We are also told that caches are initially empty, means there is nothing in there. Also assume that only accesses to matrix causes memory reference and all other necessary variables are stored in the registers. You don't have to worry about other things. Okay, so now let us see what they are trying to say here. Okay, so now let us write this matrix. Matrix, somebody said there would be 128 rows by 64 columns. So if you can tell me the 4 corner elements, I can understand that, now I can rest assured that all of you understand how this matrix would be. So let us say, I'll help you the first one and the easiest one. That the first element would be both I and j would be 0 for the first loop, loop A, right? What would be the last element of this particular row?
A of 0 of 63.
Okay, let others also think. So now, we have already said that there will be 128 rows. So, I mean, if the first one is 0, the last row would be like 127th row. And column wise, if the first column is 0th column, the last column would be 63rd column. So the first one, and as you see, the I is in the outer loop. You must have understood this from your first basic course in programming, that you first put I equal to 0, and then you go to the lower loop, and you go through this. So I00, I01, I02, I03. And when this loop is finished, and this loop will be finished when it reaches j equal to 63, and then it will come out of the loop, and that would be your first row. So we say the last element here would be a 063. Does anyone have any question in this one? Right? So this is like, this number in the second array is j. This is I. So first, you start with I equal to 0, and then you go to the inner loop, and it will just rotate through 0 to 63, and then it will be out. Just out of curiosity, what would be the first element of the second, of the second row? So let's say A. Okay, some people have already
10.
Okay, so I guess there is unanimity. And then, I is equal to 1, and then, it will rotate through j equal to 0 to j equal to 63, right? So on and so forth. So now let us look at the last one. What should be the first element here?
Sir, A1270.
Okay. So the last I, the terminating value of I would be 127. And then, it would again rotate through the value of j from 0 to 63. So this would be the last element of matrix. Now, we have been given some further data, and the further data is that this is a 4 KB cache. So we imply it that it's a 1K word cache. Now, you need to be a little careful here, because in a symbol, the IEEE committee has decided that small k in computer science would mean 1000, and capital K would mean 1024. So if I say 1 KB, I will never play this trick on you. But if you see something outside where there's a K small, that means they're talking about 1000 bytes. But because, the way the things are in computer science, which has to be in the power of 2 to make things easier. So we always talk about capital K, and that is equal to 1024. So we have got one capital K, so 1024 word cache. Okay, this is given. And let me just rub this out if you already noticed it. And I have got 32 byte of block or cache line. Both of them are synonyms. So that means 8 words. Okay. So that means in a 1000-word cache, how many blocks or how many cache lines can be accommodated? Do you understand my question? I'm telling you that I've got 1K word cache. That means 1024 words are possible to put in. I've got blocks, which is 8 word wide. So each block has 8 words or each cache line has 8 words. So how many can be accommodated here in this particular cache?
128 word blocks.
128.
2
Okay.
7.
Okay, so answer just 1 second. Okay, so what we can understand from here is that I have got 1024 word capacity cache, and my each block is of 8 word. Block or cache line, whatever you want to say. So that means I can have, and quite a few people have answered it. So that would be equal to 128 cache lines or blocks, whichever one you prefer. Now let us look at the first problem. In the first problem, when my cache, and as you know, it is clearly given that the cache is completely empty in the beginning, right? So there is nothing in it. And assume that only access to the matrix cause memory references. So all other your counter and everything is in the register. So you don't have to go to the memory or your cache. Now here you see that you are accessing elements in a row manner. So ij, right? So first element you would need so first element which I would need is A00, right? That is what is called. Now, A00 is there in the first cache block. But, as we discussed earlier, if this is missing, I need to get this element for the processor. But my block size would tell me that I would not only get A00, but I should also get A01, A02, right up to right. So this one block will be brought in. Initially, my processor asked only for A00. It was not there in the cache. In fact, there was nothing in the cache. Cache was completely empty. So the processor complained to my memory management unit and says, okay, I can't find A00. So memory management unit made sure that something is taken out from the next memory location, next lower one, and brought it to the cache. But it didn't bring just one element. It brought total 8 elements starting from A00 to A07. Now here the advantage is that after A00, next element which you are going to need is A01. And lo and behold, you are lucky. It is already brought. Then the third element you need is A02. No problem. You have already got it. Because why? Because you brought this 8 element together. And here we are taking advantage of spatial locality. That after one you need second, then you need third, then you need fourth, so on and so forth. And also, if you want to take it down to the bread slice problem, after one bread slice, you are going to have another bread slice, and it is already there. So here, this is perfect. I need the first element. So for first element, there was miss, right? A00 was not that. So my processor got a miss. But for next 7 element, what will I get? All hits, right?
Yes, sir.
Then what will happen? How many, just tell me one thing. In one row, how many cache blocks or cache, sorry, how many blocks or cache lines would I need? So first one I brought it. Total, how many of them?
8.
8.
Right? There will be total, as people say, there would be 8. And why there would be 8? Because if you see here, this is the first one. Then, the second one where I will get a miss is A08. See, I've written it this way because, I don't have a page which is large enough, which would fit 0 to 63 in just one line. But, technically, assume that this is all in one line. So the second element, now I will get a miss, is A08. Are you getting my point? The next one, when my processor asks for A08, again, that would be a miss. So my memory management unit will go and fetch another block, which is A08 to A0. What would be the last one?
15.
Right. It will be A015, right? 8 total, 8 elements you are bringing in. So whatever you have got is now, this first one is missed, but then, your A09 I will, the A09 will be a A09, sorry, A09 will be a hit. A010 will be a hit, A011 will be a hit, up to A015. They will be all hit. What will be the next miss?
A016.
Right, so now you are getting the idea. The next one to miss is A016. That is the next miss. And when you get this, you want to get the whole block, not just this element, and the last number would be A0. Come on, someone help me out.
23.
Correct. So that would be the last element. So A016 would be a miss, but then A017, A018 up to A023 would be a hit. So now you are getting an idea. So now you tell me, in getting this one row, that is 8 blocks, how many hits I'm getting? And how
So
many?
56 hits and 8 misses.
8 miss.
Sir, 1
Okay.
miss and 7 hits per row.
7 hits.
Say that again, please.
Sir, 1 miss and 7 hits per row.
Okay, you said 1 hit and 7 miss per block, right?
Yes, per
Because-
block. Yes, sir, per block.
But there are 8 such blocks in one line, in one row, right? And each block, when you bring in, so as we discussed, when we bring in 8 things, we'll get 8 misses for this whole row. Correct? Because first element would be a miss, and there are 8 such blocks, so 8 misses would be there. But rest of the elements, so 7 element per blocks would be a hit. So there are 7 into 8, 56 elements or words or data which will be a hit. Is everyone comfortable with this? Does everyone understand this? Because this is a very
Yes.
important concept.
So
Okay, I'm still giving.
A of 0 to A of 0 of 7. That's
Yes.
one block, right?
Correct.
Okay. And then there are 8 words block. That's why we are multiplying it by 8. So there are like 7 hits per block
Correct.
and 1
7
miss.
hits per block, and there are 8 such blocks, so 8 into 7.
Okay. Yeah.
Or 7
Thank you.
into 8. I mean, whichever way you want to put it.
Yeah.
Okay.
Sir,
So now, yes.
sir, this
another
these
question.
8 blocks, these blocks of 8, the first block is on cache line number 1 and the second one is on cache line number 2. Is it going like that?
No. Okay. See, what I showed you here, I told you that this up to this A063 is in just one line. I mean, conceptually, electronically, they can be placed any way, which way they like. But for us to understand, if you want to understand conceptually, you should start writing A00 up to A063 in one line. But as you can understand, I cannot fit it in my PowerPoint slide, or if I fit in, nobody would be able to read it. So I'm just putting this as first block, second block, third block, fourth block. And this is the 8th block, right? 0 to 7. So this is the 8th block. So 8 block conceptually are in one row. Here what you see is that you see them one after the other, so don't get into any mistaken notion that, I mean, this is in a second row, third row, fourth row. In fact, this all 8 blocks just form one row, but, just to make it readable, I've written them like this. Is that clear?
Okay, sir. Yes, sir.
Okay. So now this is good. Then, when you start doing this, then, you will go to the second cache line. So once you have filled up, then, the next one. Next one which you want is A10. Sorry. This should be 1. And you want right up to right? So again, the same story will repeat that, I mean, these are 64 elements, so you will require 8 blocks. And in 8 blocks, the first element would be, of course, a miss, and next 7 would be a hit. Same story would repeat in each of these 8 blocks or cache lines. So once again, 8 misses and 56 hits. And then, I will go right up to the end. So, I mean, you will keep on getting this till, you come to the last row. So again, you will get for this cache line, for this row, again, you will get 8 misses and 56 hits, again, using the same calculation. So there are certain, okay, now that we have done it, but what have we learned from this? So first of all, if someone asks me that, for getting all the rows in, how many misses will I have? So total number of misses. For bringing this, all the rows in will be how many?
128 into 8.
1024.
1024.
1024.
Okay. Someone is saying 1024. Can you tell me how?
We have
Sir, for
8
each
messages
row.
per row.
Okay, so 8 misses per row.
Into one.
And we have total 128 rows.
Per row, and you have 128 rows. So you get 128 into 8 is
1024 misses.
and the rest of them would be hits. So we have learned one thing. So now, someone asked you that what would have been the ideal block size for this. Suppose if it were in your hand to design the block size, what block size would you say is ideal for this?
64 words.
64 or
Yes,
maybe
64.
a full line.
Okay, so let us analyze your answers individually. So let us say I'm trying to design a best case scenario. This best case block size, or you can say cache line size. So someone said it is 64, right? So one whole row can be brought in. Is that correct? So this is one answer.
Sir, I think we can take 1024 means whole 1024 word block.
Okay,
Because,
the second best case block size for this problem, someone is saying we should have a block size of 1024. Is
No,
there
no,
any
according
other
to-
thought?
Sir, according to me, the
1024 into 4.
1024 into 4.
Yes, because
Okay.
we have 1024 words.
Yeah. So I'm just considering, just to clarify, I'm talking now in word size only. I'm not talking about bytes. Because I already converted words into bytes. So your 4K cache became 1K word cache. So that's why I'm talking about words. Any other answer?
Sir,
So-
according to me, it should be 8192.
Say that again, please.
8192 words.
8192
words. Because in that case, all the words of the matrix will be filled in the cache at once in one block.
Okay.
But sir, cache size is only 1K, so how can we fill this much of?
Okay, that is also something to think about. Here the limitation is posed to you by the cache size. So let us analyze this problem. See, this problem is really good for cache because you require a row and elements are also placed row wise, right? So you start going through that 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, blah, 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 up to 8, whatever, 8,192 or whatever. So that is very good. And in fact, you can also take a look at this. We are bringing this 8 words and using them all. This is not a kind of inefficient operation where we bring in a block and use just 1 or 2 words and rest of the words we are not using. So here we feel that bigger is better. And why we feel bigger, the block size is better in this particular case? Because we have stored our data in a row major format, and the need to access them is also in row major format. So that's why if we can make our cache size, or sorry, our block size as big as a cache size, so that means theoretically in whole of cache at a time only one block can remain. So that's why we are saying that this would be best case scenario and best case block size for this particular problem. Do you agree with this? So how many rows can be fitted into this 1024? Suppose if we have 1024.
16.
How many?
16.
16.
Okay. So, I hope you have done your calculation. I just believe you. So this means that at a time, if you have, this is your block size where, 1024 words are there. So you can have 16 rows present in one block, right? So that means theoretically, you will have one miss and 1,000. So, suppose if this is my block size, this is not possible because, this is larger than the size of my cache. So yes, the person who has given this answer has thought correctly that, we need 8,192 words in all. So if my block size is as big as the total thing, that would be great. But, this answer would have been correct if my cache size was larger. But here the limitation is because of the cache size, which is just 1K. So if suppose, I have put that this is my block size or cache line size, how many misses would I have and how many hits would I have? Just tell me the misses.
8 misses.
Right? So I think all of you should figure out that if I have this block size, I would have only 8 misses. And I will have, I don't know, a large number, 8192 minus 8. So whatever that number is, that much many hits. Right? So I have just 8 misses. I mean, this number is more important because, lesser the number of misses, greater it is to us, or better it is for us. So there will be only 8 misses. So this is a best case scenario where, we have stored our elements in a row format, and then, we are also accessing them in a row format. But the problem is when you want to access a column, because when you do matrix multiplication, you are multiplying a row with a column. So calling a row is very easy and very cache friendly. Why? Because, you are going to use everything. So when you bring in a block, you are going to use each and every element of that particular block. And the nice thing is you're not going to use them because, not many of you have raised this question. Probably some of you should have raised this question. And the question is, total number of elements are 8192. Okay. My maximum size is only 1024. So that means the numbers or the rows which I have put in will be overwritten, right? So the first A00 to A063 will be overwritten. So our initial thing, till we have 1024 words, you can say I will keep on putting this elements. So you tell me that how many of such rows can be filled in for 1024 word cache, and which is the first cache line which would be overwriting this. You should get back to your tag and index form. So I want you to think about this.
I equals 16 will override I equals 0.
I'm sorry?
I equals 16 will override I equals 0.
Okay, so I want everyone to think about this and then, come back to this problem because, I'm just telling you, see, I did not discuss, that, overwriting and anything simply because once I use this first elements, first row A00 to A063, I'm not going to need it again, right? Because I already supplied it and I'm not going to need any of these cache elements again. So even if they are overwritten by some other row, I'm fine, right? I don't have to lose anything. So, but theoretically, this particular cache line or this whole row will be overwritten. So let us talk by blocks that, when this A00 to A07 block would be overwritten by some other block. And I want you guys to find out which block would be first overwriting this. And to do that, you have to do this problem methodically. Find out the block size, the index size and the cache size. Cache size is already given to you. So all you need to think about is this, that, you have got this 8192 elements and, you can say that, 8291, if you don't have any other information regarding the second level memory size, then you can say that, that size is 8192. Theoretically, that is going to help you. And then, the size of this is only 1024. So then, you can easily figure out that A00 to A07 block will be replaced by some other block because, this is your cache is 8 times smaller than the minimum size of your main memory. So we are assuming that, your main memory things are stored in there. And, you are saying that, okay, at least it would be 8192. It could be larger than that. So only difference it would make is that, your tag size would change, but your index would be determined by this. And, there will be 3 bits for tag over here because this is 8 times larger than this, your cache. So which would be the first block? So someone has said that, every I plus 16th will be overwrite the element. So someone has said, and I want everyone to verify, not just take his or her answer as the final answer. So someone is telling me that A 16 0 to A 16 7. This block would be replacing this block in a first case of conflict. Okay, so I want you guys to actually check this out and tell me that, whether this is correct or not. So just by looking at the cache size and the minimum main memory size, you will feel sure that every element or every cache line in a given index will be 8 times overwritten by some new element. Okay.
Sir, here the block size is 1024, right, sir?
Say that again, please.
Sir, here the block size is 1024, right, sir?
No. That was the original, that was the problem I said for the best case scenario. What would be the best case scenario if I have this large number? So this was the best case scenario, but we are not talking about now the best case scenario. That problem is over. Now we are going back to the original thing. And when we go to the original thing, we still have our block size of 8 words. So it is A00 to A07 as the original. So best case scenario is over. Right?
Okay, sir.
We said that 1024 would have been the best for this particular problem. And, we said that, okay, since this is a general thing and, our block size is determined to be 8. So now let's get back to the ground and talk with whatever is given to us rather than thinking what would have been the best.
And sir,
what is the size of cache?
Size of cache is 1024 words, right?
Okay.
Size of cache is already given in the data, and that is 4 KB direct mapped cache. So 4 KB is basically 4096 bytes. So that is 1024 words, right? So I have converted into a word size. That this cache size is 1024 word. Is that clear?
Is 8, then
I'm sorry?
if block size is 8, then for a row, 8 such blocks can be filled.
Yes.
If we divide 128 by 8, then we get 16. So this means from A16, overwriting should start.
Okay. So, I want everyone to convince themselves by writing it properly, by writing indexes and, other things. So then, you should be able to prove it that, this is the next one which is going to overwrite it, and then which would be the next one which would overwrite this, and so on and so forth. So theoretically looking at this, I can guess that each block will be thrown out or displaced 8 times because of quote unquote conflict. So because of conflict, because 2 blocks are sharing the same index, the new incoming block which is required is replacing some block because that particular block was sitting in a spot where this particular block wants to sit. So that means they both have same index. So something has to be thrown away. So this particular block, as one suggestion is that it will be replaced by A16.0 to A16.7. I don't know. I want you guys to work on this problem because, you know, this is conceptually a very important problem. So think about this and, you know, convince yourself that, you know, which block would be replacing this particular block. And also you have to tell me that which block, each block would be replaced how many times. So that means for a given index, how many churns would be there? So how many times the block would be ejected from that particular index? So is this problem clear? So the first loop, okay. So sir, can we say that, okay, so someone has asked a question. Let me go back to that question. Can we say that we are storing the data in fully associative way? No, on the contrary, we are filling it in a direct map cache way. So one-way set associative, if you want to use that word. This is not fully associative. Even if I make, in fact, I will give that homework assignment to you. That suppose if I made this cache two-way set associative, but keeping the cache size as constant, that means the cache size is still 1024 words, but I have made it two-way set associative. So basically my index size would be halved, right? Because there will be 2 tags per index. So my cache size will shrink like this and expand like this because total cache size is going to remain constant, 1024 words. Then it depends whether you want to use 1024 this way or make it into 2 parts of 512, 512 each. And so that means 2 indexes can sit, or sorry, 2 tags can sit on 1 index. So that problem, will be giving to you as a homework problem, two-way set associative. Then, someone okay, so other people have given answer and, I want them to go and check it and write it methodically because, to get marks in exam, you have to show methodical work. You can't say that by observation, I can say this, you have to prove it to me by giving me concrete example that, okay, this block and this block, I don't know whether they do, but, if they are sharing the same index, then, this block when needed will be replacing this. And so, you have to give that answer. Now, we come down to the second loop. And that's where things become interesting. In the second block, you look at this, this problem starts over here. That, for j equal to 0, j less than 64, j plus plus, and, the inner loop is I equal to 0, I less than 128, I plus plus. So this is what is happening here. So let us write for the second block, or the second loop, I should say. So for the second loop, what are the elements, which we are accessing? Can you tell me, so what would be the first element? Let's say we are
0, 0.
0, 0.
Yeah, and that was the easy one. What would be the second element which I want?
1, 0.
A1, 0.
A1 0.
Right, the second element I want is A10. Then
A20,
A20.
And what would be the last element?
A1270.
Right? This is the last
6330.
element. I'm sorry? The last one would be A1270. Okay. So these are the elements which would be required. Now, I have a problem. I have stored this matrix in a row major format. So my first element is A00, the way I have stored it. The second element which I have stored it would be A01, then A02, A03, A063, then A10, so on and so forth. So I have stored things row wise, but I want to access a column. Isn't this a column? Right? This is the column of a matrix, and this is how I want it. So then my processor or I or the designer would be scratching their head. And I have made this problem to make it even more complicated. I say that the way the storage works or way the memory works is you have to access it just a full row, not just required block. So if you want A00, you have to get the first block, which is A00, and then A01, and then A07. So when I got this block in, my processor would be happy. So it got the first element what it needed, A00. Then it say, okay, second element I need is A10. Do you have A10 here? No. So this elements would be lying unused. To make this problem even more complicated, or just to make it look very bad, I have assumed that I have to bring in the whole row. So I have brought this block. Then, unfortunately, I have to bring the second block also, which is stored in a row-wise format. So next block I have to bring in is A08, and then A015. And I am not going to use any of these elements. So I keep on going it till I brought the last block, which has got the last element as A063. What have I done? I've used only the first element of this whole row, and the rest of them are unused. Now, some of you may comment that, this is a very bad way. Why didn't you ask for the first block? And then the next block should have been the one containing this A10 to A17. But let us just say, and that would have been the right way to do it. But let's say I have made a very cheap processor with a very cheap memory. See, now designing of a processor is very different from the design rules for a processor is very different from the design rules for physics. That in physics, you cannot violate a law. Whereas as an architect, you can do anything you like. Say, for example, you are building a house and you can make your bedroom inside a bathroom, right? You can do it. If you ask me that, can I make it like that? Then my answer would be yes, that you are an architect. You can do whatever you like. But then the question becomes, would it sell? So similarly, the designer here, I have made a design which is like, I have to bring in the whole row, whether I need all the elements or not. So I need only the first element, A00, but I have to bring the whole row. Nothing I found. So after 63 such wrong tries, the next block which I bring in, which would be, I believe, the 9th block. Correct me if I'm wrong. So Okay, so here, after bringing in 8th block, the 9th block which I bring will have A10, and then rest of the elements I won't be ever using this. And then I bring in the whole row. So can you tell me that, in doing this kind of thing or this management technique, in bringing all elements, accessing them column wise, how many misses will I get?
The same 1024.
I'm
Full
sorry.
misses. 192 misses.
Okay, so I got two answers. What do you think?
Sir, 1024.
Okay. 1024. So let us see. Where are the hits? You asked for, let's say first you asked for A00. Was it a hit? No, it was not a hit.
No,
It was a
sir.
miss. Why? Because the cache initially was completely empty. Then you wanted A10. Was it a hit? Obviously not.
No.
No.
Right? Then you wanted A20. Was there a hit? Obviously not. All these elements you brought in, this A01, A02, A07 are going to be used sometime. But here, your calculation of which row is going to remove which row is going to be important. Because by the time you actually start needing A01, that would be the first element of the second column, it would have been overwritten by something else. Do you agree with me? Because my cache size is only 1024 words. Total elements are 8192. So the row or this block which I brought in, and I thought that I'm going to use A01 eventually, right? Because this is the first element of my second column. But by the time I need this, it would have been overwritten by something else. Do you agree with that?
So, sir, in first time, we don't need A08 to A015. So, will it also store in cache?
Yes, because unfortunately, that is my strategy. So it will be occupying space in cache, but not being used.
Okay, okay.
Right? And why is that, you ask? And I say, because I am the designer and I've designed it that way. Ideal thing which you guys would say is that, just bring the block which is needed. So the first block you bring in A00, A01, A02 up to A07. And the next block which you bring in is A10, A11, A12 up to A17. But there are many low cost processors, means very, very low cost processors which may cost maybe 20 rupees, 30 rupees, 40 rupees. They do not have this expensive mechanism. So, you can say that, if things are stored row wise, this whole row will come whether you need those elements or you don't need them. Okay, so this sort of thing makes this problem looks extra bad. But, that was the purpose. So how many misses would be there? If you don't know the number, what would be your guess?
Sir, it is as a total number of elements.
128.
Okay, someone says total number of misses equal to total number of elements. That's what you said, right?
Yes, sir.
Okay. Well, so that seems to be the answer just by observation, but your job is not to give answer just by observation. Again, you have to prove to me that by the time, say, first column, I agree that everything would be a miss because none of these elements are there in the cache. So first column would be a miss. But then the second column, the elements which I need was there in the beginning. That A01 was already there because I brought in this thing. But somehow it seems to me that this block would be overwritten before A01 can be used. Right? So if that is the case, then next time when I need A01, it would be a miss because this particular block which was brought in initially would have been overwritten at least multiple times before I can use this again. So then I have to bring this block in again. I need A01. So I have to bring in the whole block, A00, A01 to A07, right? Because that's the deal. You don't get a single, suppose if I need A07, I can't just get A07 element on its own. I have to get A00 to A07 because it comes in a package. Whether you require the first element, you require the middle element, or you require the last element in that package, you have to get the whole package. Right? So here you are going to have a problem, but you have to prove to me that how many misses would be there. So this would be a good time to explain you a little bit different types of misses. Suppose you wanted A00 and the cache was completely empty. And then, you want A00 and, you will call it's a miss. But that miss would be called as a cold start miss. What we call it as cold start miss means you are looking for an element. When I say you means processor, it is not there in the cache simply because it was never accessed before, right? If it was never accessed before, the block containing that element or that word is obviously not going to be there, right? So it is not as a cold start because any element or any block which you need for the first time is by necessity is going to be a miss, and that we call it as a cold start miss. Means you are just starting. This is the first types of miss. Second is a conflict miss. Now in conflict miss, as we saw earlier in this particular problem, that when I wanted A01, this block would have been overwritten by some other block. So when I want 10 block, the block containing A01, I won't find it, but I will call it as conflict miss. I will not call it as cold start miss. Why? Because the block which I wanted or which I want was brought into the cache, but now it has been kicked out by some other block. So there was a conflict and the block which I needed was thrown out. So that I would call it as conflict miss. And the third type will be a capacity miss. So suppose the thing was there, but I had to throw it out because the capacity of cache was not that big. So the next element which I wanted to bring in, I could not because the capacity of cache was not there. So then it is called as capacity miss. So right now we are concentrating on this two: cold start miss and conflict miss. in cache 1, in the first loop, all misses, all this misses, 8 misses would be due to cold start, right? There are no conflict misses because, you know, element which is used once is never going to be used again. You are calling this first block A00 to A07, and you are going to use all of them, right? All these elements, then you are never going to use them again. So even if it is overwritten, you don't care. There is no conflict miss. So all misses in the first loop are cold start misses. In the second loop, all this first element, you know, which you are going to call, all this would be, of course, a cold start miss, but the rest of the elements would be conflict misses, right? A01, I believe, is definitely going to be a conflict miss because this number was brought in. That block was there in the cache at least at one time, but it was overwritten by some other block. Why? Because, you know, this particular block, there was a conflict, same index number. So it was thrown away. So are you getting this idea? Is there any problem? Suppose someone has said that what if we calculate in the reverse order? I don't think the problem would go away. So someone has said, I don't understand the question, got confused with the number. So can you tell me at which point you got confused in the question? Are you talking about second question? Person who has sent me this comment, sir, I didn't understand the question, got confused with the numbers. Can you just repeat your question? I mean, what exactly at which point? Okay, the second question. The second question was that basically from the loop, you can easily tell that, you know, you are going to bring in nothing but the column, right? You start j equal to 0 and then you loop through this.
Sorry to interrupt, sir, but not this one. The one with 1024 words per block. I didn't understand that part.
Okay, so why that is the best for that particular case?
Yeah, that one.
Okay, so here the thing, the word is very, the thing is very nice for us because, you know, we are bringing in a block in the first loop. We are bringing in like a block of 8 words. The first one is obviously a miss, but rest of the 7 words are hit, right? They are used up. So that gives you an idea that what if my block size was double the block size? Then, you know, if the block size was 16, then I would get the first one as miss, but the rest 15 would be hits. So then, you know, you say, okay, why not further double it? So size 32. So again, you say, okay, 1 miss and 31 hits. How about if I make it 64? Then 1 hit and 63. So what if I make it like block the whole, which would fill up the whole the size of the cache, 1024. Then you can say, okay, 1 miss and 1024 and 1023 hits. So now, you know, I have to bring in total 8192 elements. So then, you know, I will bring in the second block, which is again of 1024 words. Then again, first one would be a miss and rest of it will all be a hit. Right, so I will get total 8 hits and I'm sorry, 8 misses and several hits. So that was just a best case scenario for the first loop. That, you know, what would have been the ideal block size? I was discussing that. Do you understand that particular thing now?
Yes, sir.
Okay.
Thank
you. Does anyone have any further question? So, okay. So your homework assignment is this. Okay, there is one question I mailed it about the relationship between RAM frequency and processor memory hierarchies timeline. So the person who had asked this question was that, nowadays the RAMs are available at like 2666 running at megahertz, like 2.4 gigahertz or 2.6 gigahertz. And that RAM, is probably running at the same speed of a processor, right? Because processor are also somewhere between 3. Or for desktop, it is like 3.4 gigahertz to 2 point something gigahertz. Well, now for RAM, there are various options. It is running at 2666 megahertz or like 2.66 gigahertz. But there is something which is known as seek time. And that's what I told you. It's such a big thing. So there is something which is known as column access time. So it is calculated in terms of cycles. So it may require 10 cycles, 15 cycles, 20 cycles to go up to that or find that particular line. Once you find it, it can flow fast. And as the frequency is larger, your cycle time would be small. But if you're talking just in terms of cycles, it is going to take 10 cycles. So that means if you have like 2666, so 1 divided by 266 is whatever number of nanoseconds, that many nanoseconds multiplied by 10 cycles. So that much time would be taken. So time, absolute time would reduce, but number of cycles would remain the same. So that's why we are talking usually in terms of cycles rather than in terms of absolute time. Now, the second thing, when you are bringing in your block size, one of the reasons, I also a good thing that you asked me that, I said that, if I had my block size of 1024 words, it would have been great for the first case. But, when you bring in the 1024 words at a time, you don't have a data path which is 1024 multiplied by 32. So that many bits wide path. So your data path might be, can bring in 2 words in parallel or 4 words in parallel, not more than 8 words. That would be like huge because, 8 words in parallel means 256 bits line should be there. So then, at every cycle, 8 words would come. So to bring in 124 word, you have to wait for, I believe, 128 cycles so that you can fill in the whole block because, the calculation cannot start before the block is complete. So bigger the block size, another problem is the transport. And, that problem we will consider when we go to the later part of this. But that problem is something, you have to see that, if you make your block size too large, for some specific problem, a large block size will be very beneficial. But in general, you cannot make a block size way too large because the cost of bringing in a block is, in terms of time, is a lot, right? Because, only maybe 2 words can come in parallel or 4 words can come in parallel. And if your block size is 64 words, then, if it is 4 words in parallel, then, to make 16 cycles, you have to wait for that much time to bring in the whole block from memory to the wherever it is needed. So that is also another thing, which would waste time. Once again, in this particular course, we are doing things qualitatively. So we are saying that, okay, from cache, first level cache to second level cache, 10 cycle from second, then, further 100 cycles to go to main memory. We are using this nice round numbers just to give you a qualitative understanding of the problem. In real life, if you become a designer, then, you have to sit with paper and pen and, have to figure out the actual time. I hope that answers the question which was asked. Okay, any other question? Okay, so we stop at this particular point and we will start on